Hello. You may not know this, but your PC is probably compromised. Odds are that right now you are running closed-source spyware on your system, designed for complete remote control and perfect surveillance. This backdoor is installed at the hardware layer, making it very difficult to get rid of. So if you don't know what the Intel Management Engine is, and what it is capable of, watch the next clip. It might well be one of the most important videos you will ever see.
So, and when information about the Intel ME first started coming out, they called it a chip within a chip because it's a completely autonomous subsystem. It is not actually inside the CPU as they first thought. It's located on the PCH hub. It is completely closed source. It includes a number of modules, one of which is the AMT for remote administration. It works just like ILO for completely hardware level remote administration. It runs the Minix 3 OS. It is included in all the Intel chipsets since 2008, and some of the limited subset of chipsets earlier than that, going back to 2006. It runs on an Intel Quark 32-bit microprocessor. It has its own separate file system, which is stored in SPI flash. Some of the other modules included in the management engine are BootGuard, TPM, a DRM module, and quite a few others. So some of the capabilities for the management engine. It's active even in the power off S3 state. As long as the main power is connected, it can be activated. It has its own complete separate network and TCP/IP stack, which is completely independent of the operating system. It communicates out of band, and the OS cannot see or modify those packets at all. You might think, well, I have a network appliance, I have SEIM, I have got, Wireshark running on a separate system. But does that network appliance also have an Intel ME chip in it? The ME has full read-write access to all areas of the system main memory. It has full access to the system bus. It operates in SMM, or Protected System Management mode, so the OS cannot see or interfere with any of its operations. This is basically a God mode. It can read and write to anything on the system. If it receives a magic packet over the network interface, the AMT can be activated remotely to power on the system, change settings in the OS, change BIOS settings, view video output, do anything that a user could do sitting at the local terminal, because it's intended for remote management. You might hope that a subsystem with this much power over your system would be very well locked down and hardened in security. That is unfortunately not the case. All the way back in 2009, Invisible Things Lab developed a rootkit which lives inside the management engine in the system management mode, which can hide from the operating system any malware preventive software that you have on the operating system. It was completely persistent, could survive being, the hard drive being wiped. Back in 2010, Vasilios Ververis developed a certificate-based authentication bypass to remotely enable, deploy, and provision AMT even if it was disabled in the BIOS previously. And then here recently, just last year, 2017, the Silent Bob is Silent vulnerability, remotely exploitable authentication bypass. You just send a null field to the password, to the AMT, and you get full remote management capabilities. The AMT must be enabled, however, for this to work. This does affect not only PCs, this affects servers, firewalls, HSM, security appliances, anything on your network that has an Intel chip is vulnerable to this. Again, also in 2017, buffer overflow leading to remote code execution. So unfortunately, this thing is full of holes. This is just what we've discovered so far. It's closed source, and it's very difficult to audit. And unfortunately, Intel makes it very difficult to get rid of. We all wish that there was just a simple checkbox in the BIOS where you could just say, turn it off, I'm not using this, I'm not even an enterprise user, but they want to make it as difficult as possible. The management engine firmware is located in a region of the SPI flash memory that is inaccessible to the BIOS and the OS. The core modules are RSA signed. If the signature verification fails, it will fail to boot. They're also using LZMA and Huffman compression as a form of obfuscation. They're using a hidden directory to make it very difficult for reverse engineers to figure out what this thing is actually doing. Additionally, there's an extra IME verification module which runs every 30 minutes to check to see that RSA signature. And so if you overwrite it on boot, then 30 minutes later, it's going to check and find out that the RSA signature check fails, and it's going to shut your system down. So Intel has gone to great lengths to make it very difficult to disable this. So there has been some people that have speculated that maybe this is an intentional backdoor. NSA has a history of these kind of things. I think it's useful to play a little game of what if. So if I was the NSA and I was designing a backdoor that I wanted to be loaded on every server and network appliance in the world, what would I want? I would want it to be completely independent of the main operating system. I'd want it to be something that you cannot shut down, that can't be powered on anytime, even if the system is turned off. I'd want it to be not just stealthy, but completely invisible to anything on the OS. I'd want it to have full access to everything on the system. And I'd want it to have out-of-band communications for data exfiltration. Intel ME does all of that. What else would I want if I was the NSA? And I want to have this backdoor in every system. I'd want to have plausible deniability. I wouldn't want any evidence pointing to the NSA. I would want to have a single rogue engineer who is going to overlook a buffer overflow, who's going to overlook a remote authentication bypass. That way there's nothing tying it back to us. So what are some capabilities for intelligence gathering that such a backdoor might have? It could scrape RAM to pull encryption keys directly out of RAM. It can be used to exfiltrate data off of an air-gapped system by enabling the wireless module, even if the wireless was disabled in the BIOS and not configured. It could be re-enabled and used to exfiltrate data that way. It could also be used to infect a USB drive that was plugged in, and then that USB drive is carried to a different air-gapped system to infect that system and create a two-directional communications channel back out to the wider world.
Today I am going to show you how to disable the IME chip and install an open source BIOS on a Lenovo laptop. The compatibility of this procedure with the ThinkPad X230 that I am going to use is very well documented, so I shouldn't run into any issues. If you intend to do this on any other laptop, please do extensive research first. Okay. This is what you will need to complete this guide. A second-hand ThinkPad X230. I got mine for $130. And for 20 more, I upgraded the RAM to 16 gigs. Any regular computer, running a Linux OS. A 3mm Phillips screwdriver, to disassemble the ThinkPad. An SOIC, 8-pin test clip, to access the data lines from 2 integrated circuits in the motherboard. 6 male to female DuPont jumper wires, to connect the test clip to our programmer. A Raspberry Pi. These are the 6 pins that we will be using. Each of them correspond to a pin in the integrated circuits that are going to be flashed. To avoid confusion, I strongly recommend that you print out this schematic, and that you color code your diagram to match the colors in your 6 jumper wires. These are mine. I'll show it to you later. So I just got a second-hand ThinkPad X230. First I need to make sure that it's running the latest Lenovo BIOS. Start your ThinkPad. Press Enter. F10 to diagnose hardware. System information. The BIOS version is 2.02. I will shut down and use my Linux daily driver to visit Lenovo.com. Support. PC. ThinkPad X230. Drivers and software. Manual update. BIOS UEFI. There's a more recent version 2.77. From 2019. I will download the bootable CD, BIOS update. I will also copy the SHA-256 checksum of the file. Verifying the file. Everything is okay. I want to make a bootable USB drive out of this file. To do this, I need the package, gen isoimage. If you don't already have it, just sudo apt install it. Once you do, this is the command that you need. It is self-explanatory. Just provide a name for your output image file. There I have it. Now I need a USB drive to flash it into. Watching the list block devices command, while I plug the USB into my computer, will help me avoid flashing the wrong drive. My USB drive is device SDB. Create a BIOS bootable USB drive, with the copy command. Done. Just to make sure, I will unplug and plug the USB drive back in, while I watch the list block devices command. It worked. There's a partition on the USB drive. So unmount it. Plug the USB drive into the ThinkPad, and start it. Press Enter. F12 for boot menu. Select the USB drive. Update system program. Yes. Read that, and press Enter. Enter again. Yes. Select Yes. Press Enter. This will take a while. Be patient. Press Enter. F10 to diagnose hardware. System information. Congratulations! Your ThinkPad is on a Lenovo BIOS 2.77. Shut down, and move to your regular PC. I am going to flash a Raspberry Pi OS into a micro SD card. The easiest way of doing this, is by using the Raspberry Pi imager. You might be able to get it from your sources. I don't have it. So I will download a Debian package, from Raspberry Pi's website. Since I won't be needing a desktop environment, I will choose the Raspberry Pi Lite OS. Now I will insert the micro SD card into my computer. And select it. Click on the gear icon for advanced options. Enable SSH. And type a password for your user. Finished. Remove the micro SD card from your computer, and insert it into your Raspberry Pi. Connect your Raspberry Pi into your local network, power it on, and wait a couple of minutes. The following command will list the devices within my local network. I don't recognize this IP, so it must be the Raspberry Pi. SSH into it with the credentials you specified a minute ago. iomem. Converting a Raspberry Pi into a chip programmer is very easy. First we need to enable the general purpose input-output pins. To do this, edit these two files. config.txt, at boot. Add these two lines. And modules. At etc. Add these two lines. Lastly, we need to install the program, Flash ROM. Here we find an issue. Even though I have it already installed, my sources won't get me the latest Flash ROM release, version 1.3.0. I will have to build it from source. Start by removing Flash ROM from your system. Install the following dependencies. And clone the Flash ROM repository from GitHub. Latest Mayor release, 1.3.0. Check out to it. Type, make. Sudo make install. Great. Now shut down the Raspberry Pi. I need physical access to two chips that are soldered to the ThinkPad's motherboard, for which I will have to partially disassemble the laptop. So flip it over. And deal with those 9 screws first. Remove the keyboard by gently pushing it upwards. Be careful with the cable that connects it to the motherboard. It is very easy to detach. Just pull this tab, and it will come out easily. Next is the touchpad. This is the connector. Use your fingernail or a sharp object, and slide it between the blue tab and the black part of the connector. Pop it up. And now you can remove the whole panel. The chips we are looking for are behind the adhesive black plastic. Over here. Just peel it back, and secure it with a small piece of tape. From now on, I will refer to the lower chip as the bottom chip, and the other as the top chip. If you look closely, you will notice a round concave mark in a corner of both chips. This indicates the location of pin 1. From these polarity marks, you can figure out the numbering of all other pins by moving counterclockwise around the chips. Now we move on to the Raspberry Pi. These are the 6 pins that you need to connect to the chips. At this point it is very easy to make a mistake. So I recommend to print out this diagram, and color code all connections to match your 6 DuPont cables. As I have done. The male end of the cables will go straight into the test clip female connector. Please be sure to identify pin 1 correctly on the socket. These are the markings to look for. Once you do, you know how this goes. The last piece of the puzzle is knowing the location of the data lines on the chips themselves. Color code them accordingly, and you're ready to make the physical connections. Like this. Once you have double-checked that everything is okay, please disconnect the power cable. That would be the line connected to the chip's pin number 8.— And we finally move to the test clip. The red cable will be closest to the corner where pin 1 is located. Red cable. Pin number 1. Now you are ready to attach to the bottom chip. This is pin number 1. From this point of view, pins 5 and 8 are also visible. From this other angle, you can see corners 4, 5 and 8. All our hardware is now prepared to flash the bottom chip. It is time to turn on the Raspberry Pi again. But please make sure that the VCC power line remains disconnected. I am back to my regular computer. The following is a TLDR of what we're going to accomplish during the next few minutes. Modify the Intel Management Engine firmware image. Replacing the proprietary Lenovo BIOS firmware with an open source platform designed to perform only the minimum number of tasks necessary to load and run the operating system. Installing a legacy BIOS implementation based on Core Boot that is actively maintained and releases updates regularly. Fortunately, there's a project that manages the installation of all this software in just a couple of easy steps. Skulls. Which is what I will be using. SSH into the Raspberry Pi. Download and verify the latest Skulls release. Everything is okay. Before you start flashing, make sure that you have all these packages installed. You probably will. This script not only will disable the Intel Management Engine, but it will unlock the flash ROM as well, thus allowing internal flashing of the BIOS. In plain English, you only have to do this once. After that, you will be able to update your BIOS from the command line. No further external hardware flashing required. The second script will install the latest release of cBIOS into your top chip. And as I said, any future updates, you will be able to flash internally from your OS. It is time to connect the VCC power line. To reprogram the bottom chip, use the corresponding script. The option M will apply the ME cleaner. The option K will dump a backup of the bottom chip into a file. The flash ROM will be unlocked by default. If for some reason you want to keep it locked, add the option L. This is going to take a while. Be patient. Done. Now it's the turn of the top chip. Disconnect the power to the bottom chip. Attach the test clip to the top chip. And power it on. Run the script for the top chip. The option B specifies the board. The option K backs up the current BIOS into a file. The second option includes some proprietary software from Intel, but it will look way better in your computer screen. I will go with that. Done. Remember that you have created 2 backup files. Store them securely somewhere, and let's move on. Shut down the Raspberry Pi. And put the ThinkPad back together. Starting the ThinkPad. cBIOS. There's the Skulls splash screen. I am running Debian 12. And I have my disk encrypted. There is something slowing down the boot sequence. Let me stop right here. Pause the video and take a minute to examine this output. These logs refer to a mysterious module, called MEI_ME. The following command will speed up the boot sequence by blacklisting the Intel Management Engine Interface kernel module. I am just creating a file containing a single line. Let's try again and see what an X230 i7 with an SSD and 16 gigs of RAM can do. Pretty good for a $150 laptop. No surveillance. No remote control. No backdoor. Now I am going to show you how to update your BIOS. I will flash the top chip internally, meaning without the use of an external hardware device, just running a script. Notice that from now on, everything will happen in the ThinkPad. I am already on the latest Skulls release, so there's really nothing to upgrade. What I am going to do instead, is to make a small change to the latest Skulls BIOS, build it myself, and flash that into my chip. Let's start by cloning the Skulls GitHub repository into my system. Here's the signing PGP key. I will verify and check out to version 1.0.8. All source materials for building the BIOS are in the X230 directory. I am going to change the JPEG file, bootsplash. Next to it, you'll notice there's a bootsplash XCF file, which is the native image format of the GIMP image editing program. So I will download GIMP, and use this file as a template to create my own splash screen image. I will delete a couple of layers, and paste an image of my own. Okay, that's my bootsplash image. Now pay attention. When you are finished, you need to scale the image to exactly 1024 by 768 pixels. Now export the image as a JPEG. And click on Advanced Options. You need to unselect Progressive. And choose a subsampling ratio of 4:2:0. I will also save this XCF file next to my JPEG image. This directory contains the source code of the latest Skulls BIOS, with my own splash screen image. So let's build the BIOS from source. To do this, I need Flash ROM and Docker. The good news is that my Debian sources will get me the latest Flash ROM release. Run the build script. A directory called build has been created. Notice that it belongs to root. Change the ownership of its contents, and there you will find your BIOS ROM file. There it is, with its own SHA-256 checksum file. By the way, delete the path written on the checksum file. It points to a directory inside a Docker container that was used during the ROM file build. Now that you have your own custom-built BIOS, it's time to flash it into the top chip. Move the files into the Skulls root directory. This is the script you will use to flash internally a new BIOS. Any BIOS. Whenever there's an update, just get the ROM file and run the Skulls script. I will stop recording my screen, press enter, and show you the new boot sequence. The ThinkPad X230 you have been seeing me use in this video, I got for a little more than €100. If you upgrade to 16 gigs of RAM, install an SSD, and run a Linux OS, for less than $200 you will have a pretty badass computer. Even by today's standards. Oh, and without an NSA backdoor built into it. Keep that in mind next time you're offered an overpriced home server that runs Bitcoin stuff in it. Bye bye.